Good morning. Today what we want to do is we want to wrap up Chapter 14, our look at oscillatory motion. We've really been able to go in and look at a lot of good examples of oscillatory motion these last couple of classes. So I think we're set here. There's just a couple topics left. We may even finish a little early. We'll see what happens. We've looked at oscillations. We've been keeping track of the displacements, velocities, accelerations, and how we can work from the Newton's laws of motion in order to derive equations that tell us about how oscillations occur. So more of the same. We're going to be looking at a couple of examples that are a little more detailed mathematically. So let's go ahead and get started. So the first topic that we want to look at today is damped harmonic oscillation. Up until now, we've been looking at oscillatory motion where the amplitudes stay the same. You know, the amplitudes would be maintained, and we said that if there's no damping effect, if there are no forces that are taking energy out of the system, something like friction or something like air resistance, then the amplitudes don't drop off. Things oscillate forever. Now, a more realistic look at this would say that, you know, in reality, there's always going to be some kind of a frictional force, some kind of a drag force, some kind of a resistive force that's removing energy from the mechanical system. So if the system is left to itself and these frictional forces are in place, then you know, over time the oscillations will drop off. They could drop off very rapidly, or they could drop off very slowly, depending on how large those damping effects are. So, and the word we use for all this is damping. These are called damped harmonic oscillations or damped harmonic motion. Now, the frictional forces, mathematically, they could be represented a lot of different ways. The frictional forces, the resistive forces, can actually be pretty complicated. As I always like to say, there are people who spend their careers, you know, as engineers or scientists, studying how these damping effects might be taking place. And so we're going to stick with something that's pretty simple. We're going to say that the damping forces we're looking at are proportional to velocity. And we're going to use little b as what we're going to call a damping constant. Little b tells us how much damping or how much resistive force we have. Now, if you guys have really, really good memories, you may think, oh, we did this back with air resistance in Chapter 5. So it's kind of the same deal. The idea is that we're looking at forces that depend on how fast this system is moving back and forth. So if it's moving faster, the forces increase. Now that's not how we modeled friction. If you go back and look at friction, we said that kinetic friction was independent of the speed. So that's not quite the same way that we modeled friction. This is a little different. This is more like an air resistance effect or a fluid resistance effect that we're looking at. So what they're saying is with this damping now, we got to check signs again. We've said that keeping track of the plus and minus signs is important in these examples. So the idea here is if v is in the positive direction, depending on how we've set up our coordinate system, if v is in the positive direction, the damping force will be in the negative direction. If v is in the negative direction, the damping force will be in the positive direction, and that's what we want. We want a resistive force set up mathematically. We want that resistive force represented in a way where the damping force always opposes whatever the instantaneous direction of velocity is. And so this actually works. So for an example of something that wouldn't work is, what if we had v times v squared? If it were v squared, then whether it was the positive or negative direction, we would have the force in the negative direction. So we specifically need some kind of a function where F and V are opposite directions. Now what they're writing down then is then the mass times the acceleration will equal the net force. And the net force we have now, well, the spring is still there. So there's either a spring or it's a pendulum with a force constant. So we've still got that restoring force proportional to displacement. But now we have this additional force that we're going to call our damping force. So they're going to set up a differential equation. So this gives mass times acceleration. Acceleration now is being written as the second time derivative of the position function times, here's our new term. So what we have now is we've got a damping force given by B times V, and V is given as the first derivative, and then the restoring force, K times X. So what we're going to find is that this is one possible solution to that differential equation. So when we have a damping effect going on, what we find is, well, let's think about what the solutions looked like before. This looks a lot like the oscillatory solutions that we've been working with up until now. The only additional item that we have is we've got this exponential drop-off. Now I hope you guys are familiar with exponential functions. We've seen a number already here in Physics 4A, and I hope that you're seeing them in your math classes and you're paying attention to how they operate. So this is an exponential drop-off. This factor, specifically this exponential factor at t equals 0, becomes 1. So that just becomes 1, and then as time increases, there's going to be an exponential drop-off here. Now, what we can also show is that we've got some constants here. There's a gamma factor, which is a scaling factor which tells us the rate at which the amplitude is dropping off. So we can think now of, here is kind of an amplitude that is dropping off with time, and it's dropping off at that rate. And that gamma we can go through and show is equal to the damping constant divided by 2 times the mass of the oscillating object. The frequency is also affected. So when we add a little bit of damping, you may ask, is that going to affect the frequency of oscillation? It turns out it does. What it does is it reduces the frequency. It reduces it by an amount, b squared over 4m squared. Before, when we had no damping at all, the frequency was given by the force constant divided by the mass, square rooted. But now we've got this decrease in the frequency. Now we find out for most oscillating systems that decrease in frequency is not terribly significant. We'll see how that works. I mean, it could be. We'll see how that works in terms of frequency and the effect on frequency. So again, I just want to do my own write-up on this, I guess. So back to Newton's laws of motion. The acceleration is determined by the net force divided by the amount of inertia in the system. And so the acceleration here then can be written as, well, the net force would be minus kx, that's the restoring force, minus bv, that's the damping force. So, and then the whole thing gets divided through by m. So I've tried to fill in some of the steps here. So that becomes ma plus bv plus kx equals 0. Now, the a and the v are going to get replaced with derivatives of x. So that's what makes it a differential equation. So what we have is we have a function x, and we have a derivative of that function with respect to t, and then we have a second derivative of that function with respect to t. So to be really clear, when we write down all the formulas here, the m, the b, and the k, those are constants. They're just constants that'll have some sort of value, some amount of mass. The force constant will have a value, the damping constant. These are constants. x is a function of time. So when I look at this equation here, m and b and k, those are just kind of simple constants, but a, v, and x are going to be entire functions. So, and again, here's a picture. So here is the spring, and here is this mass sitting on here. It's oscillating back and forth. So I've got a force from the spring and a force due to the damping that's taking place. And the formulas are set up so that the force from the spring is always opposite to the x value, opposite to the displacement. And then the force from the damping is always in the opposite direction compared with the instantaneous velocity. Now this is the solution that they gave us. That works. We're going to extend that just a little bit though. So here's our formula again. Now what I'm going to do is, if you go back and look at their solution, they've got the exponential factor, they got a factor of a, they got the cosine of omega t, but what they didn't have, what I'm adding in, is they didn't have a sine omega t portion. So I'm going to put that in instead. Going back and looking at their solution, just the cosine omega t. I'm going to go in and generalize this, and the reason why is this. What we would like to do is, I would like to come up with a solution where at t equals 0, let's say that we're starting from rest. So I want to have something where at t equals 0, we're starting off at some amplitude, some starting amplitude, but we're also starting off so that the object is at rest. Now it turns out the solution that they've given us, this one, the position is equal to a when we start, but the system is not at rest. Okay, and so it turns out that this object already has motion at t equals 0. We can adjust that. We can go with a slightly more complicated function. We can add a little bit of sine to the cosine. And when we do that, I'm going to get, well, here's my displacement function. When I get the velocity function, this is the one we're concerned about, I guess. What I need to do is take a time derivative. Now, since I have time dependence in the sine and cosine, and I have time dependence in the exponential, I got to use a product rule. So I took the derivative of this. Well, the derivative of this is going to be minus gamma times the exponential. And so the minus gamma got multiplied in here. And then I got to take this times the derivative of this. And that gave us these other two terms here. So I hope I got all the derivatives taken correct. Now, what happens here is when t is equal to 0, I'm set up so that, this function becomes a. So adding a little bit of sine to this cosine and sine solution, adding a little bit of sine in there doesn't have an effect because, at t equals 0, because at t equals 0, whatever I add on here, that's going away anyway. Now, what the feature that this provides for us is now I can write down that at t equals 0, the velocity function, the one we have right here, the sine portions go away, and so in order to have a velocity that's 0 when we start out, if we want to be starting from rest, as it states right here, what I have to make sure is that the coefficients on the cosine portions cancel out. If I can get the coefficients in front of the cosines, the negative gamma a and the positive omega b, if I can set those equal to each other, which is what I'm going to do, I can get the cosine portions to cancel out. If I get the cosine portions to cancel out, then I'll be back to a solution where at t equals 0, the object is starting from rest. Okay, so that's our goal here. And I can do that by setting these equal, and then I can solve for b. So what that's telling me is I want to add this amount, that's the value I want for b. I want to add just the right amount of sine function so that the solution is describing an object that is starting from rest. Okay, what happens when we do that? Well, let me go back here very quickly. So I'm going to take b equal gamma over omega times a. I'm going to substitute it in here. I'm going to substitute it in here and here and see what we've got. So when we make that substitution, then the position function now looks like e to the minus gamma t. This is what we had before. What I'm doing is I'm taking out the b and putting in gamma over omega times a. Then I'm factoring the a out, so it looks kind of like the solution that we had before. And it says, oh, this is it. This is the coefficient that I want in front of the sine factor, or the sine term, in order to adjust the solution so that at t equals 0 it will be at rest. Let's see. So that seems like it's going to be fine. That's my new function I want to work in terms of. When I do the same thing with the velocity function, the cosine terms cancel out. So with the cosine terms, canceled out perfectly, then all I'm left with are these two terms that have sines, and then I got to put the extra factor of gamma over omega times a, factor the a out, and then I also factored out a factor of omega. So I was able to get a velocity now, that's the derivative of this function. It's minus omega a, exponential to the minus gamma t. Now that should all look familiar. But what I've got here is the 1 plus gamma squared over omega squared times sine omega squared, and that does it. So that meets the requirements that we wanted. We wanted specifically a solution where at t equals 0, x is at some starting amplitude, and that's going to be the largest amplitude this ever is at. So that's going to be the largest amplitude, and then the velocity at that point is going to be 0. Okay, so it starts from rest with just adding a little bit of sine onto that function. So let's go back and think about how much damping we can add. Now it turns out that if we add a little bit of damping, if we add a damping force that's not too big, what we're going to do is we're going to start here. This is our starting at rest, and then we go into oscillations. And the oscillation amplitude is dropping down with time. Now that's if, we can go through and show, that works if b squared is less than 4mk. So there's a particular condition that we can solve for, where as long as the damping is smaller than this, then we will have oscillations take place. But what happens if it's larger? So here they say that if it's larger, let's go back and look at the solutions that they had given us. Notice right here, when we solve that differential equation, we get a frequency that's given by k over m minus b squared over 4m squared. If b squared becomes large enough, then the argument inside the square root sign, that could become 0, or it could go negative. So that means that something else is happening. It's not going to be oscillations. If there was a way I could take a dial and just turn up the damping. So I've got something that's oscillating back and forth, and then I start turning up the damping amount. As I turn up the damping amount, what's going to happen is the frequencies are going to slow down. So the frequencies are going to get lower and lower, and at some point the frequency goes to 0, which means I no longer am going to have oscillations. If there's enough damping, if the damping is equal to or greater than 4mk, if b squared is greater than or equal to, then what happens is instead of getting oscillations, I have an exponential drop-off approaching zero. So it never crosses the equilibrium point. It exponentially drops off. It asymptotically approaches the equilibrium position, but it never oscillates. Now, there's a critical amount of damping where b squared is exactly equal to 4mk. That corresponded to the point where the frequency drops and becomes equal to zero. That also is a sum of exponential solutions, and that also exponentially approaches the equilibrium point. Now, what's interesting with this critically damped case is that that's the fastest way to get the system back to the equilibrium point. So, so we've got three possible cases here. We have a possibility of oscillations taking place, damped oscillations, where the amplitude is decreasing. We have critically damped, where we exponentially approach the equilibrium point in the fastest possible manner. Or we have overdamped, where because of more damping, it takes us a longer time to exponentially approach the equilibrium point. Okay. Now remember, everything we've done here, let's go back and see, is based on the idea that we have a restoring force directly proportional to x. Doesn't have to be the case, right? And we have a damping force directly proportional to velocity. Certainly doesn't have to be the case. And so that's why, you know, engineers they're still engineers that are spending their careers playing around with this kind of oscillation and damping effects to try and understand different mechanical systems and how they operate. So we're taking kind of the simplest mathematical approach that we could come up with. Okay, so that's the story with the damped harmonic oscillation. So here's, again, damped harmonic motion. Here is a shock absorber. So the idea with a car is you don't want it to be too rigid. So if you hit a bump, you wouldn't want the, and this applies to a lot of mechanical systems, but you know, driving in a car is probably a familiar example. We don't want a rigid car where you hit a bump and you just feel the whole bump. Maybe it breaks the car. So you put some springs in, so you can see the springs here. And then if you hit a bump, well, then you're going to oscillate, and you don't want to be oscillating down the highway all the time, constantly. You hit one bump and the oscillations last for, you know, several minutes or something. So we have shock absorbers, or the equivalent of a shock absorber. They've got a mechanical structure here with a piston down inside some kind of a viscous fluid. And so what that does is we're trying to damp things out so that the car gets back to equilibrium quickly. So we don't want that. There are systems in which damping, we don't want the damping, but they're, you know, like in something that intentionally is supposed to oscillate. But there are systems like this, with the shock absorbers in the car, where we want damping to be present. And the design here is to get as close as possible to critical damping so that the motion is damped out pretty quickly, that excess motion, and you're back to the normal distances of the car. So the car returns back to the typical configuration as to where the wheels and the axles are configured. Okay, here's an example that they've given us. I think there's one kind of like this in the homework, maybe one or two problems on damped harmonic motion. So let's take a look at this. Now, this example is a pendulum. So you go, well, you know, the damped harmonic motion applies to anything. If it's a pendulum swinging back and forth, maybe it's just air resistance, right? So it could be air resistance. It could be that this cord stretches a little bit and some energy is given off as the cord stretches. In any case, it tells us that for the simple pendulum that we have here, Um, it has a length of 1 meter, and it is swinging with a small amplitude, so we can, for small amplitudes, we can treat these oscillations as roughly simple harmonic, or I'm sorry, we can use the small angle approximation so that we can use the formulas that we have been working with for the small angle. So we're going to say that in the absence of damping, it's simple harmonic motion, and then we can add the damping in. After 5 minutes, so we set this pendulum into motion, it's only several degrees of amplitude in terms of oscillation. It says that after 5 minutes, now 5 minutes, that's like 300 seconds, the amplitude is down to 1/2 of what it originally was. So we originally set it out maybe at 10 degrees amplitude, and then after 5 minutes it's down to just 5 degrees of amplitude as it oscillates. What they're asking us is, okay, figure out what this damping scaling factor is for something that drops off at this rate. And then in part B they say, how much will the frequency be affected? Now what do you guys think? If we set a pendulum into motion and it oscillates for 5 minutes, and after 5 minutes the amplitude is down to about half of what it was, does that seem like a lot of damping? Does that seem like not much damping? And I'm gonna suggest that it doesn't sound like a lot of damping. So let's take a look at this. Here is a diagram of what x would look like as a function of t. So x here is, ooh, I wrote it as x, didn't I? So it's oscillating. So x here would represent some kind of a angular amplitude in degrees or in radians. And then here's the solution. Now we solved for that more complicated case, but it turns out for practical purposes, I mean, we could have the cosine here, we could add that sine portion on. What we're really interested in is just this part, because what they've told us is that the amplitude is now down to 50% of what it was. When we talk about the amplitude decreasing, we're really not following this oscillatory path. When we say the amplitude is decreasing, we're really thinking of this envelope. So there is an amplitude envelope that exponentially drops off, and that's given by a times e to the minus gamma t. So whether we have a cosine or a cosine plus a little bit of sine, that turns out not to be so important. We're really focusing in on this portion. So the damping constant B divided by 2m gives us this damping scaling factor. And if you remember, omega was k over m minus b squared over 4m squared to the 1/2. That's what we had solved for. Now, how do we find out what the force constant is? And for a pendulum, what we had determined was that the restoring force was mg sine theta. The displacement x is L times theta. And so those canceled out, and we were able to come up with a force constant of mg over L. Now the frequency depends on, first of all, k over m. And for the pendulum, k over m is given by g over L. That's what we had found back when we were looking at the pendulum with no damping. So the no damping solution looked like this, and then it looked like g over L to the 1/2. Now what we want to do is add the damping back in. Well, what we find is that b over 2m squared is what that extra term looks like. That can be replaced with gamma squared, where gamma is b over 2m. on the K over M side, that's going to get replaced from G over L. And so now what we've done is we've set ourselves up so that we can go in and solve for gamma. So this is the general formula for the frequency for the damped oscillations, and this is now more specifically looking at the pendulum. And then for the K over M is G over L. This is Earth, so 9.80 meters per second squared. L is 1. That gives us 9.80 per second per second. So those are inverse seconds squared. Now, they told us that this pendulum is going to operate for 5 minutes. That sounds like 300 seconds. And at the end of that 300 seconds, this factor has become 1/2. So you can see how we can isolate that exponential factor and say that's where the drop-off is coming from, is specifically this factor. That's going to become 1/2. And what I can do is I can logarithm both sides of that, and a couple lines of algebra give me gamma is equal to the ln of 2. Now it was ln of 1/2. Switching over to the ln of 2 introduces a minus sign. And so it cancels out. The minus signs cancel. I think we've used that trick before. So logarithm of 2 divided by t. So the ln of 2 over the 300 seconds says that the gamma factor here, this amplitude drop-off scaling factor, is 0.00231 per second. So every second that goes by, if we go back up to the exponential here, for every second that goes by, then this is going to be e to a larger number. Okay, 0.00231 times however many seconds have gone by, and that's going to tell us the rate of drop-off. Now, without the damping, let's go back and look at the undamped case with this pendulum. And for the undamped, that was K over M to the 1/2, which became G over L to the 1/2, which became 9.80 divided by 1. It worked out to be 3.13 inverse seconds. Now notice gamma and omega naught, they kind of have the same units. This is per second. This one is actually radians per second. Now I didn't write the radians in. I could have, but notice, in any case, radians are unitless, so we can drop those. So the gamma and the omega naught have the same factors. Now, they were specifically asking us, how is the frequency going to be affected by this damping constant? And I suggested, this doesn't look like a lot of damping. So if we take the frequency with the damping, divided by the frequency without the damping, that's the same thing as omega over 2 pi, omega naught over 2 pi. The cycles frequency ratio, with or without, is going to equal the omega frequency with or without. So that's the first thing, is I want to remind myself, yeah, I can work in terms of omega, and whatever I find out about this ratio for omega, it's going to be true for the cycles frequency also. Now, if you go back and look, let's go back and look at this formula. One of the difficult aspects of these oscillatory formulas is that there's always multiple ways of writing things. Notice that if we come back to this formula right here, now that was our general formula for damped harmonic oscillation. K over M is equal to omega naught squared. So this was omega naught, that was the frequency without the damping happening, and then the b squared over 4m squared became gamma squared. So what we can do is, I can take that omega formula that we have, I can write it this way, and this is often a useful way to represent the frequency. We can say that the frequency with the damping in place, that frequency squared, is equal to the frequency squared without the damping in place minus the drop-off factor, minus the gamma squared. So that turns out to be a handy way to write this, especially in our case, because let's see what we've got here. We've got gamma solved. So we know what gamma is. We've got omega naught solved. We know what omega naught is. Well, we could go in and just solve for what omega is. Now the problem with that is, and maybe you guys see this, I didn't write it all out. I could have written it all out, I guess. What's omega going to be? Well, omega naught's 3.13. I square that. And then I take 0.00231 and square that and subtract it and take a square root. What's my omega going to turn out to be? It's going to turn out to be so close to omega naught that I'm going to get the same answer on my calculator. Okay. Unless I keep, like, 10 or 12 significant figures. So basically what this is saying is this damping factor is so small compared with omega naught that omega is going to be really close. This small amount of damping is going to have a negligible effect on the frequency of operation. So if we want to find out by how much, and that's what they're asking us, what we could do is we could take a factor here of omega over omega naught. Now that could be written, using this formula, that could be written as 1 minus gamma squared over omega naught squared to the 1/2. And so, since gamma is tiny compared with omega naught, that factor is going to be very close to 1. It's just going to be a little bit less than 1. But that's the way I'm going to think of this. That's the factor I'm looking for. So I went in and used that to solve this. And here I'm saying very slight damping. It says that the new frequency, compared with the original frequency before we added the damping, that ratio is 0.999999728. So that's almost 1, right? That's really close. The delta, if I write this as omega minus omega naught over omega naught, what that becomes is the frequency is dropping off by an amount, or a ratio amount of 0.000000272. That's the stuff that's missing there. So the frequency is dropping off, that's the minus sign, 1 part in 3,670,000. So I would have to measure the frequency accurate to like 1 part in a million to maybe start picking up the effect. To actually observe the effect, we're going to have to be measuring that frequency really precise. So very slight damping. This factor is having a really tiny, I'm going to say negligible effect on the frequency. Now, I was just curious. I added one more question here. How many oscillations took place during the 300 seconds? We know that during the 300 seconds, the amplitude dropped off. Let me see if we can get back to a picture of this. We know that during 300 seconds, the amplitude dropped down to half of what it originally was. Now this picture only shows like 1 oscillation taking place during that time. How many oscillations were there in reality? So what I could do is I could take the omega, 3.13 per second, and I solved for the period. So it turns out that the period of oscillations for this 1 meter pendulum, simple pendulum, is 2.0 seconds. Well, it's 300 seconds that went by, so 300-second time period divided by 2 seconds every cycle gives us 150 cycles. So if I went back and looked at this diagram right here, what I would have to show is that actually there was 150 cycles that went by the time we had dropped down to half. Okay, that's a lot of oscillations in that during that time when the amplitude had dropped down. Okay, and you know, you guys have seen pendulums, so that's not a crazy amount. The pendulums tend to, you know, if you've got a bob on the pendulum that's got quite a bit of mass, the pendulum could oscillate for a long time. Okay, now the other item we could ask about is, okay, if omega naught was the frequency with no damping, and omega is the frequency with the damping in place, and gamma is kind of our damping constant, although I think we called B the damping constant also. Here's the formula that we said is handy, so when you look at these homework problems, this is a formula that you very likely will want to come back and take a look at. This actually gives us a circle. And so what we could do is I could draw a graph of omega, you know, the frequency with the damping in place, as a factor of the damping constant. Now if there's no damping at all, then you know, gamma equals 0. Well, then omega is equal to omega naught. So this is a circle with a radius of omega naught. Now what happens when we turn up the damping? So as we turn up the damping, initially it's having not much of an effect. See, the damping is increasing, but this is not dropping off very rapidly, the frequency of oscillations, even though the damping is going up. And then as we continue to put more and more damping in, it begins to drop off more rapidly. And then at the extreme value, where the gamma factor equals omega naught, then the oscillations go away. Okay, so that's a handy chart to look at. In the example we're looking at, you know, we're like, how big was gamma compared with omega, or omega naught? And it was tiny. And so we're way over here. So with the damping we added, we're just not seeing much of an effect on the frequency. So again, it's a nice graphical way to kind of judge how much damping do you have compared with what are the frequencies that you're looking at, frequencies of oscillation. All right, last topic. Ooh, okay, so we actually took a good thorough look at that. Here's our last topic, forced oscillations. So when we have systems that are oscillating back and forth, a lot of times they're being driven by some kind of a force. You guys may be familiar with the Tacoma Narrows Bridge. Maybe you've seen videos of this where the wind's picked up and the bridges, you know, buildings have natural frequencies of oscillation kind of built in. So when you're engineering a building or engineering a bridge, you have to plan for trying to eliminate natural frequencies at which the building or the bridge might go into oscillations. So what happened on the bridge is that the wind, these strong winds came through, the gusts were matching the frequency built into the bridge, and the bridge went into oscillations, and the wind continued to add amplitude to the oscillation. So if you keep pushing on these objects in a synchronized manner to the frequencies of oscillation, you can increase the amplitudes over time. And this bridge, you know, it's on video, Tacoma Narrows, take a look at it. This bridge collapses. It goes into wild oscillations. It's amazing how large the amplitude got before the bridge itself failed. And this is one very close to home here at Laney. This was just a couple miles from here. This was the 880 double-decker freeway and this is probably before, I'm guessing this was before you all were born. This is from 1989, but at the time I was not teaching here at Laney College, but I was working at the Stanford Linear Accelerator Center, and this was a freeway that I used pretty frequently during commute. And again, what happened with this was the bridges or the freeway, the double-decker freeway, had kind of a natural oscillation built into it. This freeway was built on top of landfill, and the landfill was somewhat soft, and when the earthquake hit, there's an oscillation frequency of the earthquake, and it matched pretty well some of the natural oscillating frequencies of the freeway, and the freeway was shaken and it collapsed. You know, again, the amplitudes of oscillation go up. So you can see these buildings that are that have earthquake retrofits. A lot of time with the earthquake retrofits, what it comes down to is just getting some cross structures in place to prevent those amplitudes from building up, okay, to higher and higher amplitudes of oscillation. So these are referred to as forced oscillations. Now, for the forced oscillations, what we've got is, here's the textbooks, MA is equal to here are the forces. So now we have the restoring force, that's the internal structure of the building or the bridge, and then the damping force. So there's a tendency, you know, if something begins to oscillate, a bridge or a building, left to itself, those oscillations will damp out. So there's a damping effect going on. And then here is the force that's driving everything. So the solution that they've given us now is that the displacement is given by some kind of an amplitude times, now they're using the sine of omega t, plus they've got what we call a phase angle. Now they've given us the solutions here. They're saying here's what the solutions look like. And so now we can take a look at the solutions here. I'm going to go back and actually go through a derivation. I'm going to go through it pretty quickly. You guys aren't expected to be able to do this derivation, but you know, this is something kind of interest. Where do these formulas come from? So let's go back and take a look at this forced oscillation as an example. And you know, here's the object oscillating back and forth. Now, what's happening here is we're driving these oscillations with some kind of a force, but it's varying with some frequency. So it's not like we're just pushing on something in one direction. We push it in one direction for a while, and then we pull back. And then we push on it, and then we pull back, and then we push on it, and we pull back. Now, as you might imagine, any of you who have pushed someone in a swing, if you push them and pull back with kind of a natural frequency of that swinging person, you can get the amplitudes to go really high. If you're pushing at a frequency that doesn't match the natural frequency, then the amplitudes are going to remain pretty low. In order to transfer energy in, I need to be able to push on the object while it's moving in one direction and then be pulling back when it's moving in this direction. If you think in terms of work and energy transfer through work and power, that depends on the force being in the direction of motion of the object. So if the force lines up with velocity, so if the force is in the same direction as the velocity, so here are the formulas for this forced oscillation. We've got all the forces set up here divided by the mass. We're driving this with a force that varies like a cosine or a sine function. We're going to use cosine here. And then omega is the frequency of the driving force, okay, as we've been talking about. So that's what the formula looks like. Now we've got two different ways we could represent these oscillations. One would be to go ahead, this is the textbook approach, what they're doing is they're setting up, now I'm going to switch over and call the amplitude big C, and we'll see why that is. That would give the displacement in terms of a sine function. Now the velocity, this is the one we're really interested in, is how is the velocity, how does it compare with the force? Is the force in phase with the velocity? So if the velocity and the force are synchronized, we're going to be transferring a lot of energy, and the amplitude could go up and up. If the velocity and the force are opposing each other, that's actually going to slow the system down. So again, depending on what the frequency is of the driving force compared with the natural frequency of the mechanical system. So here is x, v, and a, velocities and accelerations, using the phase angle approach. Now what I'm going to do instead is instead of using a phase angle, I'm going to take the displacement, I'm going to add some cosine onto that. So that's two equivalent ways of looking for the solution here. I'm going to go ahead and add a little bit of cosine, so we got cosine and sine, and that means that the solutions look like this. Now what I've done is I've eliminated the phase angle, and I've done everything in terms of sines and cosines. Now at the end of the day, we can switch between these two solutions, because whenever I take a sine and a cosine and I add those together, what I can do is I can take the coefficient and I guess it's the velocity that I want to be looking at here, so let me specifically focus in on velocity. I can take the A, which is giving me an amplitude for the velocity, and then I can take a B and use that for the sine function, and then I can use Pythagorean's theorem to see what C is going to be. So if I take a certain amount of a cosine and a certain amount of a sine and I add them together, what I'm going to end up with is a squared plus b squared equals c squared. All right? And then the phase angle I can get by taking the tangent of b divided by a. So this would work. This I prefer because at the end of the day I can just match up all the sines and cosine factors. I don't have to bring in trig identities in order to solve the problem. So anyway, so two different possible sets of solutions for going in and solving this. Just a reminder, the phase angle is phi, and what that represents, whether or not the force and velocity are synchronized or whether they're not synchronized with each other. That's what we're looking for, is are those two in phase or are they out of phase? And then the net amplitude then would be given by, here we go. So here is the original formula. So I'm going to take those expressions for x, v, and a, and I wrote those out. Now, from looking at the formula above, I can see that with x, whatever I come up with for x has to be multiplied by a factor of k. And whatever I come up with for v has to be multiplied by b, and whatever I come up with acceleration has to be multiplied by m. So what I'm going to do is I'm going to take a look at this sine factor, and this one, and this one. I have to add all these together. I'm going to get 3 contributions to the sine. Now the sine all added together give me coefficients of minus, minus m, or m times minus omega squared times a, and that's what I wrote here. And then moving up to here, I've got b times minus omega b. See, there's that common factor of sine omega. And then finally up here, there is a sine contribution, which is k times a. So I took all of those and said all of those coefficients on the sine have to add up to be 0. And that's because if I look at this side of the equation, there's no sines over there. So those all have to be add up to be 0. Now the remaining terms, here, here, and here, those all have to add up to be f, because I have a cosine on this side. So again, the reasoning here is if I look at everything on the left side, it's some combination of sines and cosines. All the sines on this side, all their coefficients have to add up to be 0 because there's no sines on the other side. If I add together all the cosine terms combined, they have to add up to be f. So that's giving me these two equations. Now what I can do is I can take equation 1 and solve for a in terms of b or b in terms of a. So that's what I've done there. And then what we can do is take the second equation, which looks like this, and I can start substituting things in. So on this one, I took out the b and substituted in that expression for in terms of a. So b is being substituted with this expression. When I solve for a few lines of algebra here, I'm getting that the coefficient for the coefficient a is going to be f times b omega over all this stuff. When I do the same thing for b, I get a very similar looking at equation. You can see how those are kind of complementary solutions. And then if I take a look at the net amplitude comes from taking c is equal to a squared plus b squared, whereas the phase angle is equal to tangent of the phase angle is b over a. What that gives me is an overall amplitude of f. Now this was a squared, maybe b squared. A squared plus b squared, and then they had the same denominator to them. And then we had to take an overall square root. So this is the same solution that the textbook has. We've shown how that was developed. So what it says is that I'm going to get some amount of amplitude that depends on how much force I'm using to drive this. This term right here, we'll take a closer look at this. This is the frequency at which we're driving it. And then this is the damping term. And then here is tan of phi. Now, what we can do with this then is we can come back and say that let's track this down. Here we go. So there's a natural frequency, which is omega naught, and omega naught squared is equal to k over m. That means that everywhere I had a k in my solution, I can replace that with m omega naught squared. And so our final solutions look like this. The amplitude depends on the force times this whole expression square rooted. And that includes the mass and the difference in frequencies. Now I've labeled this as resonance. Resonance has to do with, well, what we were talking about before. Am I pushing this with the, am I driving this in a manner where I'm matching the frequency, the natural frequency of the oscillating system? If I do that, if I match, here's the frequency I'm driving with, here is the natural frequency of the system. If I match those, then this piece in the denominator gets very, very small, and all that's left is the damping effect. So as I remove the damping effect, that's one of the effects we're talking about here. If I get rid of all the friction and I drive the system very close to its natural frequency, the amplitudes get really large. Okay, and so that's what we're, in some cases, we want to efficiently transfer energy to something that's oscillating. In other cases, we don't. We don't want an earthquake to efficiently transfer its energy into a bridge or a building. So there, what we want to do is try and make sure that whatever frequencies earthquakes occur at, that those don't correspond to the natural frequencies of the building or the bridge. We want to build the buildings and the bridges so that their frequencies of oscillation don't match up with something that might set them into motion. You know, wind effects from the wind or from earthquakes. And then here are damping effects too. So dampeners can be added to buildings or bridges, for example, so that if they do go into oscillations, is there a way to damp down those oscillations? So those are the two effects that we're after here in solving for this. And again, this is, there's no homework problems on this. This was just something, textbook certainly included in it, and has a very good description of this. So I just wanted to provide some background, some other foundational information for that. So here's what the frequencies look like. If we're driving this with some external frequency, when we hit the natural frequency, the amplitudes are going to go up. So that's what this is representing. How large are the amplitudes of the oscillation? So as we get very close to the natural frequencies, it's going to get a lot larger. Now this also has to do with damping. So if there's not much damping in the system, then we'll get lots of amplitude around the natural frequency. If there's a lot of damping going on, then it doesn't really matter so much if we're at the natural frequency or not. In that case, the damping is the dominant effect. Okay, here's a more carefully drawn diagram, and there's what's called a Q value, which tells us the quality or the effectiveness of energy transfer taking place. And again, there are systems where we do want the energy to be transferring efficiently, but there are systems where we don't want that to be happening. If it's a musical instrument, we're trying to design it in a way where a lot of the energy transfers into generation of sound coming from that instrument. If it's a building or bridge in an earthquake, we don't want the energy to go into the structures that we've built. Okay, and that wraps it up. So if you guys have any questions on this, stop by, let me know, and let's take a look at those questions and get whatever questions you've got answered. As always, make sure you're staying caught up with everything in the course. And again, for today, a couple of those later topics today, especially the forced oscillations, you want to have an understanding of those, but no need to do the detailed mathematics of that. That's all for just interest if it's something that you want to take a look at. So you'll be seeing some of this stuff when you're taking differential equations. You'll come back. I think that some of this stuff is some of the examples that they like to go to in differential equations, I hope, because they have such excellent engineering and physics applications to them. But so, you know, if you've taken differential equations, this stuff, you know, may be something that you want to go back and look at in some detail. If you haven't taken it yet, then, you know, this is your first pass through this, and it gives you a chance to see what you will be encountering in some of your math classes in the future.